Okay, so this is a recording for the sample assessment material, Edexcel, that you've recently done. I'm going to focus on paper 2, section A, which is the statistics content. I am going to quite quickly go through how you should respond to each of the questions. If you do have any further questions, make sure you do come and ask. Try-nows will follow. Question 1. Sarah is investigating the variation in daily maximum gust for Camborne in June and July 1987. She used a large data set to select a sample of size 20 from the June and July data for 1987. Sarah selected the first value using a random number from 1 to 4 and then selected every third value after that. State the sampling technique Sarah used. The clues in the question are the fact that she chose a random number in between 1 and 4, very small selection to choose from, and then every third value. From that, I know that we're talking about systematic sampling. Okay, so I wasn't asked to describe it, I was just asked to state what sampling technique it was, and it was systematic sampling. From your knowledge of the large data set, explain why this process may not generate a sample of size 20. Okay, so we've looked at data sets before, and what sometimes happens when we get a data set is that some data is actually missing. So I may not get a sample size of 20 because for each of the values that are chosen, there may not actually be any gust data. There may not be any daily maximum gust data. And that's what stops us from getting the sample size of 20. Well, that's what stops Sarah anyway. Okay, so next we're told that the data Sarah collected are summarized as follows: n equals 20, the sum of t equals 374, and the sum of t squared equals 7,600. Calculate the standard deviation. All right, great. We've been given some summary statistics, which is going to make our life a little bit easier. We're going to go ahead and find that standard deviation. 3 things that I need to find ahead of that. We're going to need to find x bar, which is going to be the sum, in this case, the sum of t divided by n. We're going to want to find s of xx, which is going to be the sum of t squared minus n x bar squared. And finally, we should be able to go and find standard deviation, which is going to be the square root of s of xx divided by n minus 1. So those 3 things we need to look out for. Let's go ahead and find them. So x bar is going to equal 374 over 20, which gives 18.7. Okay, from there I'm going to find the s of xx. So we're looking for 7,600 minus the n value here is 20. So I'll use the fraction here, 374 over 20 squared. All right, so once again into the calculator, and that leads to 606.2. And finally, standard deviation I'm going to find by looking for the square root of both of those values, 606.2 over n minus 1, n was 20, so that's going to be over 19. And that will lead to 5.6485, and that will be my standard deviation to 4 decimal places, guaranteed my accuracy there. So setting out the equations that I needed to use, substituting my values, and just using my calculator sensibly, and that should be worth all of your marks. Question 2. The partially completed histogram and the partially completed table show the time to the nearest minute that a random sample of motorists were delayed by roadworks on a stretch of motorway. The actual question here says estimate the percentage of these motorists who were delayed by the roadworks for between 8.5 and 13.5 minutes. Okay, so for us to find that percentage, we're actually going to need to know the total number of motorists that are involved. At the moment, there are 2 gaps that we're going to need to fill. So here and here, we need to find those values. Using the histogram, I should be able to find the frequency density, which is going to lead to me being able to find the frequency. Firstly, something that a lot of people neglect. If we look here, in between the first class, 4 to 6, and the second class, 7 to 8, these are not the actual class boundaries. There cannot be any gaps in a histogram, and the diagram shows us actually that that first class actually goes from 3.5 to 6.5, and those are the true class boundaries. So we had a bit of a clue there that these are actually the values that we should be using as class boundaries, and these are the ones that we should be using to calculate class width. All right, so now I've got those values in there. I should be able to use the first bar as an indicator to what the frequency density will be. My calculation for frequency density is those 6 motorists divided by a class width of 3. 6 divided by 3 gives me an answer of 2. So I know my frequency density at this point for this particular bar would have been 2. Okay, that's enough information to fill in the rest of this scale. Scale's complete. Can I use that to find these missing frequencies? So the second bar, to find its frequency, I'm going to take the class width, which is going to be 2. So that is a class width of 2. I'm going to take the class width, which is going to be 2, and I'm going to multiply it by the height, which is 7. 2 times 7 gives me 14. So the frequency here would have been 14, and we'll jump straight to that last class. The class width there is 5, and the height is 1, so the frequency must be 5. All right, so now I actually do have all of the values there. I can find out how many motorists were involved altogether. A quick count gives us 96. There's 96 motorists altogether. Okay, and back to the question. I was asked what percentage are between 8.5 and 13.5. Thinking on the table, which of these need to be included? Well, this group starts at 8.5. So I want to include all of those. This group will also be included. And only part of the next group is going to be included. But what part of the next group? Well, since I want to know up to 13. Just going to quickly add that to the diagram. There's my 13.5. What fraction of the whole bar is this shaded part? Well, the width of this shaded part is 1, whereas the width of the entire bar was 3. So this is actually 1/3 of that bar. So I'm going to need to find 17 plus 45 plus 1/3 of that 9, and I want to know what is that as a percentage of 96. So adding those together, I'm going to get 65, and so I'm looking 65 over 96 as a percentage. We'll use the calculator to do that, and we're looking for 67.71%. So finding the frequency density, really thinking about what those class boundaries were going to be, and using those to find unknown areas allowed us to be able to find out the amount of motorists that we were interested in, and therefore to find the percentage that responded to the question and will get us all our marks. Moving on to question 3. The Venn diagram shows the probabilities for students at a college taking part in various sports. A represents athletics, T for tennis, C for cricket. P and Q are unknown probabilities. All right. The probability that a student selected at random takes part in athletics or tennis, so right here, athletics or tennis, is 0.75. Find the value of P. Athletics or tennis is going to be anywhere inside of this circle or inside of this circle. Everything shaded represents people who take part in athletics or tennis. Well, if I know that that's 0.75, I'm going to use that with the fact that all of these probabilities should add up to 1. So I know 0.75 plus 0.05 plus P equals 1. And with some smart rearranging, even just doing it in your head, we get that P equals 0.2. So a nice little 1 marker to warm us up. Okay, so next we'll ask to state, given a reason, whether or not the events A and T are statistically independent, showing all working clearly. Firstly, since we know the value of P, let's place each of these 0.2. All that's left is what is actually the value of Q. Once again, if all of these are meant to add up to 1, or if the union of A and T is meant to be 0.75, that means Q must be 0.15. All right, so let's just fill in those first. No unknowns left. We're working all with numerical values. The test of independence is if the probability of A multiplied by the probability of B equals the intersection of A and B. If this is true, then A and B are independent. Okay, so let's just test that out. Probability of A is 0.35 and the probability of B 0.6. If I multiply them, I get an answer of 0.21. Is that the intersection? 0.21 does not equal the intersection because the intersection was 0.2. The fact that it's close does not matter. It's not good enough. This does not equal the intersection. Therefore, A and B are not independent. And finally, find the probability that a student selected at random does not take part in athletics or cricket. So, if they do not take part in athletics or cricket, I'm looking for everyone outside the athletics circle, everyone outside the cricket circle, and I can see from that the probability that they're not part of athletics or cricket is just these ones on the outside that we can see, and it's 0.45. So be careful to know exactly what regions of the Venn diagram the question wants you to use, which ones are useful for you, and how you're going to combine them together. Setting it out like this, potentially highlighting or redrawing the Venn diagram, clarifies exactly what you're thinking of, and that will be worth all your marks. Question 4. Sarah was studying the relationship between rainfall and humidity in the UK. She takes a random sample of 11 days from May 1987 for liqueurs from the large data set. She obtains the following results. Sarah examined the rainfall figures and found these quartiles. A value that is more than 1.5 times the interquartile range above Q3 is called an outlier. Show that R equals 20.6 is an outlier. So we're talking about this value right here. Show that is an outlier. Okay. An outlier is anything beyond Q3 plus 1.5 times the interquartile range. So let's find out what that value is. 2.4 is my Q3. The interquartile range I can find by doing 2.4 minus 0.1. And all of that into the calculator equals 5.85. Okay, so is 20.6 an outlier? Well, it's definitely bigger than 5.85. So since 20.6 is greater than 5.85, it is an outlier. Be careful to make sure that you state this. Just finding the 5.85 is not enough to show that you know what to do with it. Finish with a sentence. Since 20.6 is greater than 5.85, it is an outlier. All right, so we found this outlier. Give a reason why Sarah might include the outlier, and then give a reason why Sarah might exclude the outlier. Well, the outlier was a piece of data that we found. Just because it's a large value, is that enough for us to decide that it's not going to be included? I'm going to go ahead and say, so since it was one of the data points, it should actually be included in the data, regardless of if it was extremely large or not. Okay, it could also be argued that this may have actually been an error that was made when the data was being input into the system. So for that reason, it could be justified as being excluded. These outliers can be argued both ways as to whether to include or to exclude, and it might actually take a little bit more investigation to determine and decide whether or not to include your outliers. Okay, so Sarah decided to exclude this day's readings and drew the following scatter diagram for the remaining 10 days, giving interpretation of the correlation between rainfall and humidity. Okay, so here, yes, it looks like there may be positive correlation, but it's not enough just to say positive. That would be stating the correlation. An interpretation, I need to link humidity and rainfall. All right, so here's my interpretation. As humidity increases, rainfall increases. Now that is interpreting the positive correlation. The equation of the regression line of R on H for these 10 days is R equals negative 12.8 plus 0.15 H. Give an interpretation of the gradient of this regression line. Okay, well, the gradient is right here. It's the 0.15. Okay, once again, it's not good enough just to state the gradient. We need to interpret the gradient. The gradient is how one thing changes as the other one does. So for every extra 1 of H, R is going to increase by 0.15. More formally, okay, so for each percent that humidity increases, rainfall increases by 0.15 millimeters. I just went back to check what was the unit for humidity, it was percentages, and what was the unit for rainfall, it's millimeters. So I can incorporate that into my response. For each percent that humidity increases, rainfall increases by 0.15 millimeters, and that's going to be worth all of the marks. So next we're asked to comment on the suitability of Sarah's sampling method for this study. The sampling method was to take a random sample of 11 days from May 1987 for liqueurs, which is just one place in the UK. She was meant to be studying rainfall for the entirety of the UK, but she's only chosen one place to take measurements from. How do we know whether or not that's going to be representative? Also, she's only taken 11 days out of the whole year 1987. I think she could take a lot more readings in terms of the different days, so we get a spread of the whole year, and a lot more different places in the UK. Okay, so Sarah's sampling method is not appropriate. That's my response to part one. Comment on the suitability. And my suggestion to Sarah is that actually she needs to take more readings from more locations within the UK and on more than just 11 days. All right, 11 days is a very small sample size. She needs to increase that sample size to get a more representative sample for her study. So on top of that, she could have actually tried to use all of the data if she'd used a computer system to help her with the analysis. All right, so how could she have improved or made better use of the large data set, computer system, or just get more data? So be careful to be very specific about what you're recommending that she does. If you're going to be vague, you risk not getting what you deserve. A response like this that refers to more locations within the UK and the more days is going to be what you need to achieve all your marks. Okay, and moving forward to number 5. The discrete random variable x follows a binomial distribution where n equals 40 and p equals 0.27. Find the probability that x is greater than or equal to 16. A couple of things to note. So right here, this probability, I know that's not going to be in any available tables, so this is definitely a question you're going to need to use your calculator for. Also, I have a greater than or equal to probability, and we know straight away we can't calculate, or our calculators are not set up for greater than or equal to. We're going to need to do a 1 minus straight away. Let's write in that 1 minus statement. This will be worth a mark in itself. The rest of it is just typing into the calculator, and we end up getting 1 minus 0.9491 to 4 decimal places, and that leaves us with our final answer, 0.0509. Okay, 2 marks in the bag. Moving on, past records suggest that 30% of customers who buy baked beans from a large supermarket buy them in single tins. A new manager suspects that there's been a change in the proportion of customers who buy baked beans in single tins. A random sample of 20 customers who had bought baked beans was taken. Okay, any clues in the question? 30%, that's what's going to be our p-value. There's been a change, all right? All he said is there's been a change. He hasn't stated whether it's an increase or a decrease, so that is my clue. I'm working with a two-tailed test. And we know we have a sample of 20 customers. So we'll come back to that. For now, let's state the hypotheses. All right, so H0, I'm looking at the probability that a customer buys baked beans is 0.3. And for H1, it's the probability that it is not equal to 0.3. All right, so what we're gonna do from here? Okay, let me just state that P equals the probability buys a single pack of baked beans. All right, let's just not forget exactly what that stands for. Using a 10% level of significance, find the critical region for a two-tailed test to answer the manager's suspicion. You should state the probability of rejection in each tail, which should be less than 0.05. All right, I used X earlier in the question, so I'm just gonna use Y for now. Y follows a binomial where N equals 20 and P equals 0.3. Straight away, I wanna know what the expectation is. And since this is a hypothesis test where we're trying to find the critical region, let's see if a diagram can help us out. So it's two-tailed. This is a critical region. This is a critical region. I'm looking for the value here and here. I'm looking for the value here and here. One of each of those is going to be significant, whereas the other is not going to be significant. All right, we're given a 10% level of significance. So I know that in each of these, that should be 0.05. That should be 0.05. And even the fact that we were told 0.05 here is a clue that we're doing a two-tailed test. Okay, so the probability, looking in my tables or using the calculator, I know 0.3 and 20 are very table friendly. The probability that X is less than or equal to 3 equals 0.1071. And the probability that X is less than or equal to 2 equals 0.0355. So here we have what we're looking for, 2 consecutive values for the cumulative frequency, where one of them was significant, being less than 0.05, and the other was not. That lets me know that actually these values this must have been the 2, because the probability that is less than or equal to that 2 is smaller than 0.05, and this must be the 3. Probability is less than or equal to 3 is greater than 0.05. Okay, let's do a similar thing, but for the top end now. So the probability, choosing a smart value in looking at the tables, try and track down something close to 0.95. So the probability it was greater than or equal to 9 is 1 minus the probability that it's less than or equal to 8, which is 1 minus 0.8867, which turns out to be 0.1133. Okay, so that's greater than the 0.05. What about greater than or equal to 10? That's 1 minus the probability that x is less than or equal to 9, which equals 1 minus 0.9520, which ends up being 0.0480. Okay, once again, what we were looking for, one of them was significant, while the other one was not. That lets me know one of them is on this side. This is going to be the 10, and one of them's on the other side. That's going to be your 9. Okay, so I've tracked down those values, but I was asked for the critical region. Those probability statements are not enough for me to have the critical region. I'm going to need to say which values as outcomes will lead me to reject H0. So it's this inequality statement that we're looking for. It's this inequality statement that we're looking for. Unless you write this by itself, you're not going to get credit for getting this far. All right, so x is less than or equal to 2, or x is greater than or equal to 10. These are the two ways that I will reject H0, and I'm going to put the union system, the union symbol in the middle, just to show that actually it could be either of these two for my critical region. Okay, let's just box that off as the critical region. Okay, next I'm asked to find the actual significance level of the test, and I'm really just going to add the probabilities of the critical region. So what was the probability that x was less than or equal to 2? It was 0.0355. What was the probability that x was greater than or equal to 10? 0.0480. Adding those together, 0.0835. But significance levels usually come as actual percentages. So what is this as a percentage? 8.35% is the significance level. So moving on. One afternoon, the manager observes 12 of the 20 customers who bought their baked beans in single tins. All right, so our observed value right here is 20. Comment on the manager's suspicion in the light of this observation. Really, the question is this significant or not? Well, it is in the critical region, meaning that actually there's enough evidence to reject H0. So there's evidence to support the manager's suspicion. Okay, be careful to make sure that you state all of these things here. It's not enough to say the manager was correct. That will not get you your mark. You need to let us know what 12 lets you know, or what's the significance of 12. It's in the critical region. It leads to the fact that we can reject H0, so that's your mathematical conclusion, which then leads on to the fact that we have evidence to support the manager's suspicion, which is the contextual conclusion. You must have these parts in there to get the mark here. Okay, finally, later it was discovered that the local scout group visited the supermarket that afternoon to buy food for their camping trip. Comment on the validity of the model used to obtain the answer in part E, giving a reason for your answer. Okay, now that I know that there was actually a scout group who are a lot more likely to buy single tins of beans, while we were conducting the investigation, it seems it may have changed our results unnecessarily. Why does it no longer fit with the binomial distribution? Well, there's some conditions for the binomial. Firstly, there should be a fixed number of trials, constant level of probability, and the binomial distribution has to be independent. And these customers, these scout members, were not independent of each other as they came into the shop. They all came in to buy the same thing. If one of them bought beans, they were all buying beans. Okay, and because of that, the binomial is no longer a good model to use, and the conclusion that we made earlier, it may not be valid those observed values, those observed customers, lots of them were Scout members or could have been Scout members, and that makes the binomial no longer a valid model. Be careful to be specific when you're responding to these context questions. You need to make sure that you're going to be awarded the credit that you deserve. So a response like I've shown will be worth all your marks.